Welcome to the demo session of FPGA based signal processing system. My name is Ranjan Tiwari and I am a PhD scholar working under the guidance of Professor P. Sumati in the Department of Electrical Engineering, IIT Roorkee. I will be introducing you to the platform Altera based programming, Altera boards, how the softwares can be installed and how programming can be done, and finally how it can be transferred into the board or dumped into the board. So let me start by introducing you to the platform. So first we have to install the Altera Complete Design Suite software. What it will do, that it will automatically introduce two basic tools like DSP Builder, which is used to design the FPGA implementable programs, and the another one is the Quarters software. So the Quarters will be it is like a tool to synthesize the these blocks and it can be transferred into the FPGA boards. So let me start by first introducing you to the DSP Builder environment. When we install this into the MATLAB, so first we have to start the Simulink block. So let us say I am starting any Simulink program. So I have started here MATLAB program. So I will be opening the Simulink. So for any basic program, what I will be doing, that I can open this Altera DSP Builder advanced block sets or Altera DSP Builder block sets, which is shown here. So for opening any new, either I can open a existing profile files through this open model, or I can create a new file through the new model. So let me create one file, basic file. So and the blocks can be taken from this side. Like these are the Simulink environment, basic Simulink environment. So first this is the advanced DSP Builder block sets, and this one is the Altera DSP Builder block sets. So in this, if we see, there are many blocks. They are categorized into this different block sets. So this one contains all the basic blocks which are DSP Builder implementable, and this is the Alt Lab. So this contains another different blocks. This is the arithmetic blocks like adder, subtractor, and all multiplier and all these things. This contains all the board related functions. So here we can find the board which I am currently using, like Altera Stratix 3 board. So if you can see Altera Stratix 3 EP3SL 150, this is the board, and all the components related to this, it is shown here. I can drag these blocks and right click basically, and it can be dragged into the any file. Add to untitled it is showing, because right now I have not named the file name right now. So let me start by giving a basic example. So I will be searching any let us say I will be searching any constant value. It will take some time. So if I right click here on the constant, I can directly add it to the add to untitled. So you can see that this has been added to the this programming. Now what I want to do basically is simply show you how it can be shown onto the scope or something. For that I can here search here display. I can also use scope. So here I can right click, or I can drag also this one. I can drag and drop this block to here. So let me connect. The connections can be made basically this like this. I can directly run this without saving also. For simulation it will work, but for hardware implementation we have to save and then compile it. So let me try to run. So we can see the constant value has been displayed on the display. So rather than doing this all the programmings, I have already done some programming and I will be showing it here. So I will not be saving this file. Cancel. So I will be introducing you to two basic programs, like how we can configure this ADC and DAC. So I can give the input to the ADC pin, and I will be taking the output from the DAC pins. So here we can see, so for the hardware implementation, we are using all these hardwares. This one is the NI Elvis 2 Plus board. It is basically used for designing the analog filters on analog systems. So we are using basically one op-amp to give the signal. This DSO is used to give the signal also and to take the input signal also, to display the signal also. It has the 4 channels where the signals can be displayed, and this is basically the Altera FPGA board. So these are the connections to the PC through which it can be programmed. This is basically the power supply of this FPGA board. These are all the peripherals associated with this FPGA board. So we can see here that this is one HSMC card associated with this board, and there is already also one more slot which can be also connected, but right now we are using only the one slot. So this is this one has 2 ADC pins and 2 DAC pins. So if you see this one, this is ADC 1, this is ADC 2, and now this one is the DAC 1 and DAC 2. So for programming this one, I have already done a basic programming. Let me open this file. So this is like ADC DAC ADC to DAC conversion basic program. So these are the clock block which has to be given for configuring this clock signals, and it will be taking the 50 megahertz clock. So the time period it is shown like 20 nanosecond. The second one is the signal compiler. It has to be used for compiling all these programs, and these are the configurable blocks which are used for ADC to DAC conversion. So this is the basically Altera Stratix 3 board icon. It has to be used to program the overall structure. So first I will save this one, which is already saved, and I will try to compile this one. It will be going through all the steps. Like first it will analyze the program, then it will be like fitting these programs, synthesizing, and then it will take some time, like 1 minute or something. Then it will be ready to deploy on the FPGA board. So it is going through all the steps. So now the fitting has been completed. Now the optimization has started. So this shows the running of this compilation program. If the compilation will be completed, then it will stop. So now we can see that the program has been compiled, and I can scan this one. So it will be connecting with the FPGA board. So it has been already taking this one as through the USB blaster. The board name is EP3SL150 chip name. Now I can directly program this one. So the program has been dumped into the FPGA board. We can see that we are giving the signal from this signal generator. So it has been connected to first to this board. We have designed one buffer circuit basically. So we are giving this signal to the input of this buffer, and we are taking the output from the buffer. So we can see we have connected this one to the ADC signal, ADC port here, and also since we are taking to display this signal to channel 1, so we have to use this buffer, otherwise the loading problem will occur. So we are simultaneously giving the input to this ADC, and we are also showing to the channel 1, which is the yellow signal. And if we see, we are taking the DAC output basically. So we are converting this signal from giving it to the ADC and then converting to the DAC. So right now I am using the DAC 1. So this is like DAC 2. So this second one is used. So if you see, the blue one is showing the DAC 2. So if I show you by stopping this one, we can see the whatever the signal we are giving, it is simply passing the signal and giving the output. It can be shown by I will sliding this one lower side. Okay. Okay. So this is, we can see whatever the signal we are giving, basically we are trying to extract it from the DAC. So this is a basic ADC DAC program which we have shown here. Now I will show you how to program a SDFT, Sliding Discrete Fourier Transform program. So I will be closing this one. The programming now this is the Sliding Discrete Fourier Transform. So again we are connecting this input signal to the A to D, A to D to the second ADC, and then we are passing it through the binary point casting. What happens that when we give the signal to the ADC, it will be shifting. It is like signed values. So it will be in the plus side also, in the negative side also. So what we have to do, that we have to truncate this signal so that it can be passed through the to the program. So rather than putting it to the 819 to upper side and 819 to lower side, we use the binary point casting to reduce the amplitude of the signal, and then after some gains are used, and this is like signal tapping. We can also tap the signals and see on the tappings. So this overall program is to reduce the sampling frequency basically. If I do not use this one, then the overall program will be working for 50 megahertz signal. So it will be very high frequency. But right now what we are doing, that we are dividing this clock signal, 50 megahertz clock signal, with the 20. So right now the sampling frequency will be giving, this block will be giving the sampling frequency of around 2.5 megahertz. So 50 megahertz divided by 20, almost around 2.5 megahertz. So the signal is first passed through this delay to register the signals, and this part is the comb filter. So this the first n xn minus xn n minus m. So this is like xn minus n. So the endpoint basically SDFT. So n is taken here as 128. After that, this signal is passed to the resonator. So this overall part is the resonator. So we can see first it has one delay, and this delay is multiplied with the 2 cos theta. So this is 2 cos 2 pi k by n. K we are using here as 1, n we are using 128. Now after that it is passed through the second delay, and it is multiplied with 1. So this is the comp part, this is the resonator part, and then after we are converting this signal into the in phase and quadrature phase basically. So this part is used for in phase, and this part is used for quadrature phase. And then we are using two DAC blocks, these two DAC blocks, to display this signal to the DSO basically. So these are like 8192 samples. We are XORing this one to since the this DAC will be giving the unsigned values. So what we are doing, that we are shifting from lower side to the upper side by XORing this signal to the 8192 samples. So I will be compiling this program, and then I will be showing it to the FPGA board and the DSO how it is working. So again, it is going through all these steps. Fitting, timing, and all these steps will be again. It will take 1 to 2 minutes, and then it will be compiled, and then we can dump this program to the FPGA board. Filter placement operation beginning. Fitting has started now. Now optimization has started. So the program compilation has been completed. So the board is already connected, so no need to scan the again. We can directly program. So while we are programming, so it will not show any output. So only input is shown, which is yellow one. As soon as the program will be dumped here, the input and in phase and quadrature phase will be generated. So we can see it has been programmed now. So if I stop this one, okay, so the green one has moved this side, I think. Wait. So the first one is the yellow one is the input signal, and the green one is the in phase signal. So I can show you by merging these two signals. I have to increase this one. Yeah. So the green one is the in phase signal, which is almost coinciding with the input signal. The blue one is the quadrature phase, which is 90 degrees shifted. If I increase the amplitude, so it can be seen that the SDFT is working properly, and it has been able to extract the input in phase and quadrature of the input signal. So the input signal we were giving like 19.53 kilohertz signal, which is shown here, wave chain. So 19.53 kilohertz signal was given, and we are able to extract the in phase and quadrature phase of the input signal. So in this session, I have shown how a basic programming can be done on the Altera based environment, basically on the DSP builder, and I have also shown you two programs. One is basic ADC DAC program, in which any signal can be given from the outer environment to ADC, and it can be taken through the DAC and shown to the DSO. And the second program is basic SDFT program. So SDFT can be used to extract the input frequency of the any input signal. So the input signal which we gave was 19.53 kilohertz input signal, and its in phase and quadrature phase has been extracted, and it has been shown to the DSO. Thank you.